is looking at the list of participants. Is there anyone?
Yes.
Okay.
I think we should switch to English.
Shamil.
So I can speak in English, yes.
Yes, okay, thank you.
Okay, thank you. Thank you very much for inviting me here. It's a pleasure to be giving a talk. I think this is my first maybe talk in depth on this subject. So the subject is called quantum DELL system and around. It's devoted to a particular multi-body integrable system. It's a quantum system. So it will be given by differential operators, and since it's trigonometric and actually elliptic, it's not going to be differential, but it's going to be difference operators. In fact, it's going to be difference operators of infinite order, as expected from an elliptic integrable system, which is elliptic not only in the coordinate, but also in the momenta.
Is it double elliptic system? What DELL stands for?
Yes, sorry. Yes, so DELL is a shortcut for double elliptic system.
Is it one particle or multi-particle?
Multi-particle, it's an n particle.
Okay, thank you.
So here is a plan. I'm following the paper, which is given here. It's a paper by myself and Peter Koroteyev, was out in year 19, where we constructed a system of operators, difference operators, which compute, and which is double elliptic, which means that it's elliptic in the coordinates in the momenta. I will describe the basic properties of that system in the first part of the talk. I will then pass to eigenfunctions and comment on what are the eigenfunctions of this system, what is known about them, basic properties of these eigenfunctions, and so forth.
Shamil, excuse me, I just missed more, maybe. Is the classical double elliptic system is known? The last time I saw it was just one particle system.
That is an excellent question. So it's known for one particle. In fact, there are several different constructions for one particle.
Yeah.
And then for n particles, it's a little bit more hypothetical. But by now, there exist some constructions for higher number of particles as well.
Okay. Thank you. I was afraid that I missed some moment when the multi-particle system was.
Actually, the classical case is more or less one of the points of consideration in the third part of my talk, which says comparison to known results.
Okay, thank you.
Sure. So I will consider in detail the case of SU2, which is very enlightening. And I will first specialize our general results to the case of SU2. There is going to be a very nice formula that comes up as a result. And then I will compare this formula to the known formulations for the classical DELL system in the case of SU2. And then I will comment briefly on what are the problems with comparison with other approaches and so forth. I will then consider two special cases, the case of so the DELL system has two elliptic parameters. One is called omega and the other is called p. And I will consider two limiting cases, the case of omega equals to 0 and the case of p equals to 0. So this parameter governs ellipticity in the momenta, and this parameter governs ellipticity in the coordinate. So one of these systems is well known. It's called elliptic Reginaar-Schneider. It's a famous and useful integrable system. It's actually this one. The other one is kind of less known. I think maybe it's even fair to call it a new integrable system. It's elliptic in the momenta, but it's trigonometric in the coordinate. According to the very useful comment which has been given by Morozov et al. In one of the recent papers, it's not actually fair to call this a dual elliptic Reginaar-Schneider. dual elliptic Schneider has similar properties, but it's a different system actually. And then I will conclude the talk by saying a few words about one similar system in representation theory, which is also double elliptic, but curiously for which the Hamiltonians, the explicit form of the difference equations, is unknown. And there is these functions in representation theory have been developed by Ettinghoff et al. And there is a conjecture that the eigenfunctions of our DELL system should actually match the functions developed here, modulo perhaps some canonical transformation, which means modular multiplication by some function, or maybe something similar to this. This is completely conjectural, and in fact, we don't really know how this works. But we expect there to be a match. Okay, so I will start. So the origin of quantum DELL system and sort of the starting point that I want to start from is trigonometric Schneider model. This is a famous n-body integrable system. The coordinates of the particles are labeled xi, and actually everything is trigonometric. So you should think about every variable that you see as being an exponent of the physical variable. So really this x is an exponent of the physical coordinate of the particle. And similarly, pi is the exponentiated momentum. So it's not really the derivative, but it's rather a shift. And as denoted here, it's a shift by some finite parameter q, which also should be thought of as an exponentiated variable. And then operator xi is tautologically the operator of multiplying a function by xi. So these two operators, the exponentiated momenta, which are sometimes called rapidities, and the exponentiate coordinates, act on functions of n variables x1, xn in the following way. And they are canonically conjugate, again, in the exponentiated sense. So px is xp times this factor. And you can easily recognize it as the canonical conjugation relation for the exponentiated form of the coordinate momenta. In particular, this means that if the indices are different, then they simply commute. Having said all of this, the main statement about the system at the level of the quantum Hamiltonians, HK, is that the quantum Hamiltonians commute identically on all functions, acting on all functions of n variables. This is easy to check and also not hard to prove. This has been proven for a long time. So this is a quantum integrable system. What can be said about it? Well, one thing that I want to say before going further to the next slide is that this is a deformation of the not less well-known integrable system, which is the Calogero-Moser integrable system. And you obtain the Calogero-Moser integrable system in the limit when you pass from shifts to derivatives, which means that you go from a trigonometric to rational integrable system, which means that all of the exponentiated variables have a small parameter. For example, you can think about xi as e to the epsilon xi, where epsilon is a small parameter which is responsible for the trigonometric deformation. And then when you send epsilon to 0, you recover back the Calogero-Moser Hamiltonians, which are going to be differential operators now.
But what is t parameter in Calogero-Moser?
It's sometimes called beta. There's one parameter, right?
In front of.
Is it related to coupling constant?
Yes, that's the coupling constant of the Calogero-Moser. Indeed, you can see that if t is equal to 1, this is going to be trivial. So the system decouples.
Are the wave functions known?
For the trigonometric model or for the rational one?
For the trigonometric.
Yes, I will speak about this in just a second, but maybe in 3 slides. But before I speak about this, I want to first talk about elliptic deformations. So the subject of this talk is the DELL system. And the main statement is that actually a DELL system should be thought of, or can be thought of, as a double elliptic deformation of these trigonometric operators. There is one deformation in the coordinates. It is kind of straightforward. Namely, if you as I emphasized several times during this slide, if you think about all variables as exponentiated variables, then this difference here is nothing else but a sine function. It's basically e to the argument minus e to the minus argument. So it's either a hyperbolic sign or the usual sign, depending on what you think about complex properties of the argument. And if you replace the sine function, which is one single periodic, by a theta function, which is double periodic, then this will give you an elliptic deformation of this model. And this, in fact, the correct elliptic deformation. It's what is called elliptic Ruzhner-Schneider. It's elliptic in the coordinates, and it's still trigonometric in the momenta. The second deformation is much more intricate and has been open for many years. And we have a suggestion for the double deformation, which switches on both this elliptic deformation of the coefficients of the operator, which is easy, and the elliptic deformation of the shifts, which is a little bit harder, or quite a bit harder. To see how this works, I want to show this simple example of n equals to 2. So this is a case of actually, I would say, 2 particles, because there are 2 positions, but there is a trivial degree of freedom, which is the center of mass. And if you remove it, then you can think about this as an integrable model with 1 degree of freedom. So it has been long suspected that this model has a double elliptic deformation. And I will show what is the reason to suspect this and how to switch on the second deformation, most importantly. So this operator, this is the example of the previous slide in the case of n equals to 2. There is only single Hamiltonian in this case because it's a model with 1 degree of freedom. And it can be written in this form, and it can be ellipticized in 2 different ways. So before doing this, I want to rewrite this by taking the common denominator out here. And then the numerator, you can see that I added some extra eigenterms proportional to P1, P2. This is related exactly to the center of mass degree of freedom, and it's trivial in the sense that a Hamiltonian P1, P2 commutes with this Hamiltonian H1. And also I added a unity, which is also trivial. So, but this is really simple. Modulo these simple additions, the Hamiltonian can be, the numerator of the Hamiltonian can be written in this way. And also can be written in this way. This is identical. This is the same function, the same polynomial. What I did is I grouped different groups of variables. I grouped sines, as I discussed previously, sine functions, which depend on the coordinate. And here I grouped instead sine functions which depend on momenta. There is more or less only one way to do this, both here and here, because if you group sine functions depending on momenta, then you see that it should be linear in the x variables, and then there are only 2 x variables, x1 and x2. So it should be a linear combination of x1 and x2. And when you see what is the coefficient of x1 in the above expression, it's going to be factorizable as a product of two sine functions. So it's really neat and nice in this simple SU2 example. And now you can already see what I'm suggesting. I'm suggesting that if the elliptic deformation replaces sine functions, which are single periodic, by theta functions, which are double periodic, then this expression suggests a very nice elliptic deformation in the momenta. Namely, you replace these sine functions here and here by theta functions. And this is going to be an elliptic operator in the shifts. It is an infinite order difference operator that has as many shifts as you like. So it's in other physical jargon, it's non-local. You never end up with a finite amount of shifts. You're always shifting to all the way to infinity. And here are the two deformations that I'm talking about. So the first deformation is we're replacing the sine functions in the shifts by theta function. Sorry, in the coordinates by the theta function. And the second deformation, we're doing this in the shifts. So here I'm introducing the main theta function notation in this paper. It's going to be probably unconventional for some.
And your elliptic p parameter has no relation to momenta.
Elliptic p parameter is a constant, and it's a new constant.
It is not related with momenta at all. Yeah, it's just some strange notation.
It's not really. Oh, I'm sorry. Yes, it was kind of historical for a line of papers until this paper, so we didn't want to change it. So these p's and this p is just it's probably useful to denote this as capital P's. So these p's and this p have nothing to do with each other. This is a constant, and these are operators. Thank you.
Shamil, looking on these formulas, I see that it's in the first one, it's elliptic, certain in coordinates, but it's still polynomial or just not elliptic in P, and vice versa.
No,
It's supposed to have,
trigonometric, of course, trigonometric.
it's still origin. Okay.
Exactly. This is elliptic / trigonometric system. So I'm showing how to switch one deformation without switching on the another.
Sorry, another question: in which space of functions the second Hamiltonian acts?
It's really the same. It's not much different, because you can easily see that if you act on monomials, so if you act by the second operator on any monomial, then this operator acts by simply multiplying the monomial on some constant multiplier. So it's well defined on monomials at least. And then it's well defined on polynomials, and it's well defined on power series.
Thank you.
You mean formal powers, or
I think you can go more. I think you can do more than that. Really, this operator is well defined because you can define it on any function here. It's not going to be multiplication by q. No, I think yes. If you care about analyticity properties and things like this, you really need to say that this is well defined on the monomials, and then see what you can construct from monomials. So it's really you have to take care probably on what is the class of functions indeed.
Thank you.
You don't have to take care though if you're considering formal power series in the modular parameter of the theta function. So that is the case when you can simply work with finitely many shifts, because when you expand the theta function in the modular parameter, or in the exponentiated modular parameter, then you only having finitely many shifts at every given order in the expansion. So in this way, you can prove, as this is what the main result of our paper with Peter is we proved that corresponding Hamiltonians commute in the first few orders in the expansion in the new parameters, in the new elliptic parameters. And for this, we didn't really need to take more precise care about what is the space of functions that we're acting on.
So you mean that you will present for multi-particle case some Hamiltonians and check their commutativity when expanding in P, which is downstairs, yeah?
Yes, and there are going to be two different P's. Because the system is going to have two different elliptic parameters, one in the coordinates and another in the momenta. When you switch this deformation, this doesn't work very well. When you switch the first deformation together with the second deformation, the elliptic parameter has no reason to be the same. There are going to be two different elliptic parameters. And what you said, Andrei, is precisely correct. We're expanding in these two elliptic parameters, and we're checking that the corresponding operators commute order by order. This is already new, because in principle, you can consider operators which are valued in power series up to certain order in, say, P, by saying that, for example, you can do a trick, and you can declare that P to a certain order vanishes identically. So you work in a ring of functions of the form of power series in P modulo relation P squared is 0. And
but then it's not elliptic, right?
But it's still a new operator.
Yeah, it's a new operator, but it's not elliptic anymore, if you do like that.
Sure, but we are not proving any double elliptic properties at the moment. This is going to be global. So what we're doing, we're suggesting an explicit expression for the Hamiltonians, conjecture that it's double elliptic, and conjecture that they commute. And then we prove that as power series expansions to the first few orders in these parameters, they indeed commute. Of course, in the first few orders, you won't see any global properties. That's true. Okay, so I will continue by now. I'm happy that this discussion happened, because indeed there are a few things to discuss here, and I'm happy that I put the slides in the talk so that we can discuss these issues in a simple example. So once again, this theta function is an exponentiated notation for the Jacobi theta function. I write it's a version of the Jacobi theta function, because there is a second version, which we are going to need shortly. Indeed, you can see that this formula is nothing but a triple product formula for the Jacobi theta function. So here Z is the exponentiated argument, P is the exponentiated modulo parameter. And if you take a look at the expansion in the parameter P, you can see that in the 0th order, this function starts with 1 minus Z. 1 minus Z is not quite a sine function. More closely, it would be a sine function if you would have Z to the minus a half minus Z to the plus a half. And so this is exactly the second version of the Jacobi theta function that we will need. It's different from this one simply by multiplying by Z to the minus a half. The advantage of the second version is that it's going to be an odd function in Z.
Sorry, may I ask about this first Hamiltonian?
Yes.
So what is the space of functions it should act on? In a sense that, is it true that acting on just monomials, we can get something non-trivial?
No, the first Hamiltonian, I don't think there is any problem with discussing what it acts on, because you can define the action on any formal function f of x1, x2. You see, the first Hamiltonian has only finitely many shifts.
Yes, but if you want to find its eigenfunctions, what is the correct answer to do this?
This I will talk about in a few slides, but I can say immediately that in every finite order, so the zeroth order Hamiltonians are, or the zero order eigenfunctions in some coordinates can be written as simply polynomials. And then in every increasing order, you will have Laurent polynomials. But the degree of the Laurent polynomial will be bound by the order of expansion in the modular parameter. So this would be a well-defined class of functions.
So no elliptic polynomial is just some expansions in modular parameter.
So far, yes. And actually, these functions will be closer to theta functions themselves.
Thank you.
There is one other simple example that I will also show. It's probably easier to just move on and actually show these examples rather than announce them. So let me continue. Okay, so this slide is the first non-origin slide, and this is the slide where I show you the Hamiltonians that we constructed with Peter. So these are Hamiltonians which depend on 4 parameters. There are 2 trigonometric kind of parameters, Q and T, and there are 2 elliptic kind of parameters, P and W. I say this because the trigonometric parameters were present already in the trigonometric model here, Q and T. T is the parameter which is related to the coupling constant, or how the coordinates in the coefficients talk to each other. And Q is related to the magnitude of the shift, or the action of the rapidities or momenta, exponentiated momenta on the eigenfunctions, on the functions. Now, the other 2 parameters, P and W, are going to control the ellipticity. P is going to be the elliptic parameter in the coordinates, and W is going to be elliptic parameter in the momenta. There are 4 parameters. In the limit, when you switch off both elliptic parameters, you're reducing to trigonometric Rudiner-Schneider model. And further, if you send Q and T to 1, keeping their ratio, or not the ratio, but the ratio of the log of the logarithms constant, you're reducing to Calogero-Moser. And then you have only a single parameter, which is exactly that ratio. We suggested the following formula. So I will first present the formula, and then without explaining where we got it. And then in a few slides, there's going to be motivation, and sort of I will explain how we actually found that formula. And not surprisingly, we found it from the relation to physics / algebraic geometry of moduli spaces of instantons in supersymmetric gauge theories in 4, 5, and 6 dimensions. But all of this is not necessary to at least appreciate the result. So we consider the following power series, O of Z. This is a generating power series for some quantum operators OK. You have in every order in the Z variable, you have an operator. The sum goes over O integers, as you often see in conformal field theory. It's defined as a sum over the lattice of the nth power of the of Z.
What is large n? Is a number of particles?
Yes, large n is the number of particles. Of the generating parameter to the sum of these variables of the summing that we're summing over. So on the lattice, the sum controls the order of the operator OK. And then the quadratic form on the lattice, this quadratic form given by a simple sum ni times ni minus 1 over 2, controls the degree in the elliptic parameter omega. And then you have a shift operator to the power, the first shift operator to the power n1, and so forth, the nth operator to the power nn. So you see that these indices that we're summing over are just simply the powers of the shifts. And so far, I've said nothing but just the fact that this is an operator, which is an infinite order operator in the shifts. You have shifts to every possible order that you can think of. And then in every order, there is some coefficient. And then our result with Peter is that we suggest the explicit formula for these coefficients. The formula is, well, you have this prefactor, which controls the dependence of the coefficient on the counting indices and on the elliptic parameter W. But then you have the dependence on the coordinates, and that is given by kind of a shifted Vandermonde determinant. It's a product over I less than j of theta function in the parameter p. And note that here you have two parameters. Parameter omega enters here, and parameter p enters in the theta functions. Of t to the ni minus nj, this is a shift in the Vandermonde, and then you have xi minus xj, xi divided by xj. So this is a typical trigonometric Vandermonde shifted by this factor, and then actually ellipticized by theta functions here. The star in the definition of the theta function is exactly what I was talking about on the previous slide, is that it's extra x to the minus a half. So that theta function star is an odd version of the Jacobi theta function. Sorry. So this defines the operator O completely.
I missed what means this star. Is this multiplication you mentioned, or?
No, star is very simple. It's not this function. Here I'm denoting it without a star.
Yeah.
But it's this function
But this is also odd, right?
Not in the exponent of z.
But if logarithm of z equals to 0, it has a 0, right?
Sure, but if you send z to z minus 1, it multiplies by a certain factor.
I see.
And this factor is exactly what we want to eliminate.
Mm-hmm.
And
this is just odd theta function written in this multiplicative variables.
In the multiplicative variables, exactly.
And when p goes to 0, yes, it gives us elliptic Ruginars.
It would give elliptic Ruginars if omega goes to 0.
Oh, okay.
And this is
if p, because if p goes to 0, it looks more nice.
It's nice in both cases. I will actually showcase both cases according to my plan in this fourth point. This is, if p goes to 0, this is going to be a dual model. It's a new integrable system, which is elliptic in the momenta and trigonometric in the coordinates. It's not elliptic Ruginars because elliptic Ruginars, as we seen, is elliptic in the coordinates and trigonometric in the momenta.
And these Hamiltonians, these operators, okay, so it's actually a ratio, yeah, of two such operators, which look like some theta functions, or?
Yes, so if you take the modes of this current, so this is a current, it's a generating function in Z, and if you take modes, then ratios of modes remarkably are commuting quantum operators. So the modes themselves do not commute. We cannot claim that OK prime commutes. They don't. But if you take a ratio, if you normalize by operator O0, then what you get is going to be the quantum Hamiltonians of some integrable system. That is exactly the quantum DELL system.
But O0 is just some multiplication of theta function without t, yes?
Not quite. Not quite. If you take a look at this formula, O0 is a non-trivial operator that has infinitely many shifts.
Yeah, they just differ by condition to the sum of this n small.
Exactly.
Yeah. So and O0 just when
Okay,
when
we have negative ends. Okay.
yeah, they have. Mhm.
Even though if you restrict the power of omega as well, then the condition on the quadratic form will produce for you meaningful restrictions on the indices ni. There is going to be finite set of indices which contributes to every order in omega.
Sorry, I missed. What is O0? We have seen negative powers in the sum. Yes. O0 is a zeroth term. I see.
Zeroth term, yes.
Sorry.
Okay, so
Are X and Z related?
No, Z is a formal generating parameter, and you don't even have Z in the Hamiltonians.
So Z, okay. So Z appears only at front of the summand.
Z appears.
No, I mean on the right.
Which summand?
Like you sum over Zn, Z appears only in the first multiple. I'm sorry.
In other words, Z is a replacement for the index K in the Hamiltonians. So there are many Hamiltonians. They are labeled by an integer index K, and instead of that K, we're introducing in this formulation a continuous index Z. The relation is that this is a generating function in K with respect to Z. So that's you can think about this as a Fourier transform, but this is too complicated probably. It's just simply a generating function.
Yeah, I see.
Okay, so I will continue. So the main statement about these operators HK is that they commute as power series in the extra parameters P and W. And we checked this up to quite high orders in P and W, and we even checked this in exactly in P and in a few orders in W. So that would be a sort of generalization of elliptic Ruzhina-Schneider in a few orders in W, but exact in the P parameter. And so the question is probably the most interesting question is how to prove this in all orders in P and W. And there is one strategy that goes through the relation to physics/geometry. Then there is a different strategy, which is direct computation using the properties of theta functions. And I'm sure that more clever proofs will appear in a few years, probably. So I want to talk now about eigenfunctions of the system. There is no mystery because this is a deformation of the system that we know about. The eigenfunctions should be the deformations, also the two-parameter deformations of the system that we know about. And the system that we know about is the trigonometric Ruzhina-Schneider system.
Shamil, one question.
Yes.
Eigenfunctions in what space? Is it just formal solution to the equation, or what is the space of functions? Where it can go?
So for the trigonometric Ruzhina-Schneider, it's the space of polynomials, literally.
Mm-hmm. Polynomials in Q?
In X.
Oh, in X, okay. And for elliptic? And for elliptic?
For elliptic, so if you switch on only W, they are going to be still polynomials, so literally the same. If you switch on both, you will start getting Laurent polynomials, but at every order in P, the degree of the Laurent polynomial is bounded. So this defines for you a certain class of functions.
So, but in the periodic, in trigonometric case, they are trigonometric polynomial in X. So as a function of X, they are periodic, right?
Yes.
Mm-hmm.
Yes,
Thank
these
you.
are exponents, actually.
Yeah, I'm sorry. And why you choose this concrete space of functions? I mean, I understand that technically it's motivated, but does it motivate from physics or something? Because to me, it seems like some unnatural space of functions which defined in perturbation series.
No, trigonometric polynomials are.
No, I mean that you define that the definition of space of function depends on perturbation series in P. Well, you said that the power of Laurent polynomial depends counts by P. Yeah.
Yes, and it's bounded by P, and in fact,
Yeah.
the theta function itself has this property.
Yeah, but can it be formulated without referring to perturbation series in P?
Well, what I checked is that you cannot express the eigenfunctions through theta functions alone.
So eigenfunctions could be expressed in terms of theta functions. They sum up to them, right?
Sometimes they can be expressed in terms of theta functions in simple cases, but generally I don't think so. And so global space, I still have no clue. I only have the clue in perturbation theory and in the values when the value of the P is small. So in the power series P.
Sorry, Shamil, you mean theta function of x variables?
Yes.
And on which, so what are the modular, what are the period matrices for these theta functions?
P.
P?
Small p.
So elliptic functions of x's, yeah?
Yes, eigenfunctions look roughly like elliptic functions of x's with parameter p.
Mm-hmm. And you say sometimes, yeah?
Yes,
sometimes.
Mm-hmm. But this is an important case, and it kind of, even though the exact theta function dependence disappears generally, the behavior in perturbation theory is the same. So as you add degrees in P, you gain a little bit of Laurent terms, and they are bounded by the degree in P. This is exactly the theta function behavior. It's a very interesting question, what are the global properties of these eigenfunctions? I haven't seen a single consideration on this subject so far.
But do we know eigenfunctions, like in any closed form, eigenfunctions of elliptic or quantum resonance, or we only have a perturbation theory for that? So why we are starting at these functions and not eigenfunctions of elliptic resonance, which should be
to the best of my knowledge, for elliptic resonance, we only know perturbation theory for eigenfunctions.
Okay, thank you.
There may be some integral formulas. This is related to the last point here, similar system and representation theory. That similar system, which we expect to match our system, has an integral representation. And that would be a global formula. That would be a global expression. But the relation between our eigenfunctions and their functions is conjectural. So I cannot say anything useful at the moment. But what I want to say is that if you consider the case of trigonometric operator, then the eigenfunctions can be written as trigonometric polynomials, which are none other than the infamous MacDonald polynomials. MacDonald polynomials are the two-parameter deformations of Schur polynomials, which are characters of unitary groups. Characters of unitary groups are naturally trigonometric polynomials because the eigenvalues of a unitary matrix are lie on the unit circle. So if you consider irreducible representations of a unit of the unitary group, they are labeled by highest weights of these representations, which are essentially Young diagrams, which are these increasing or non-decreasing sequences of integers here. And then for every irreducible representation, you have a character, which is a trigonometric polynomial called a Schur polynomial. And further, each Schur polynomial has a MacDonald deformation, which can be defined in many different ways. There is combinatorics definition. There is definition from physics. There is definition from geometry of quiver varieties. There is a definition from integrable systems theory. So this is exactly the definition. If you consider these Hamiltonians, then the polynomial eigenfunctions in the as deformations of Schur functions will be given by MacDonald polynomials. So MacDonald polynomials have arguments x, and they are labeled by Young diagrams lambda. Here are two examples of MacDonald polynomials, one for SU2 and the other for SU3. This corresponds to third symmetric power of the fundamental representation of SU2. It's a four-dimensional representation, and it's a four-dimensional representation, and consequently there are four terms in the polynomial, and you can see the MacDonald deformation from the Schur point. The Schur point corresponds to t equals to q. I'm spending so much time at this discussion because this Schur point, the case when MacDonald polynomials are reduced to characters, is going to be exactly the only case when I can globally solve the eigenfunctions of the DELL system in terms of theta functions. This is the case t equals to q. It's remarkable here, you can see that when you put t equals to q, all of this becomes unity. And this as well, this is the same number. So you get a simple sum of four terms with unit coefficients, which is a character of a four-dimensional vector space, and these exponents have the meaning of weights. And similarly for SU3, this is going to be this polynomial in representation 2, 1, which I think is the adjoint for SU3. It's 8-dimensional, and is it 8-dimensional? 1, 2, 3, 4, 5, 6, 7. Okay, this is not very much. This is not very important. This is some representation of SU3, and there might be a misprint in this formula because I don't really remember a 7-dimensional representation for SU3, but at least structurally it's correct.
Should be 8-dimensional, like a joint. So it should be
yes,
two.
but there are 7.
Okay. Maybe last term is 2 is
Exactly.
equal to 2 for q.
This is stupid. Yes, of course. Wonderful. So this is the character of the adjoint in the limit when t is equal to q. Okay, so these are two examples of MacDonald polynomials. Note that the first example suggests an elliptic deformation again, is that each term is factorized, and you can in principle replace these sine functions by theta functions of the corresponding argument. It's not guaranteed that it's going to be any reasonable eigenfunction of any integrable system, but as I will show, in fact it is. This exactly is the eigenfunction of the omega deformed elliptic model. And then when you switch on the p deformation, then this polynomial is going to be turned into a Laurent polynomial, and you will have Laurent terms growing from both sides of this polynomial bounded by the degree in p. And this is the best that we know about elliptic eigenfunctions. This is an example of a double elliptic eigenfunction, actually. So this is the fundamental eigenfunction for SU2. It's a deformation of the fundamental character. And then in every order, as I promised, you have a Laurent polynomial. But the degree is bounded. So this is fairly explicit. I write terms in first order in P, and then I write mixed terms, which is the most interesting. The first double elliptic term here is this one. This is first order in P and first order in W. No single elliptic system has such a term in the expansion. So almost nothing about this formula is interesting except for the Laurent behavior. It's just some power series. So you can check to this order in P and W that this is indeed an eigenfunction of this Hamiltonian. Yet this example, this power series approach allows to is useful because it allows to come up with conjectures. So as an example, I will show you how to conjecture the main global result that we have. Indeed, what one can do with this formula, you can see complicated rational functions in T and Q here. What one can do is one can put T is equal to Q. So specialize to the sure case. And then in the sure case, you can check that actually these complicated rational functions become unities. And this actually even becomes 0 because there is an explicit T minus Q factor here. So what this means is that in the case when T is equal to Q, the W dependence drops out. Also not surprisingly, because as I said, there is a natural way to ellipticize these polynomials by replacing their coefficients with sine functions here. And if the coefficients are unities, there is nothing to replace. Unity, elliptization of a constant is a constant. So if you don't have any sine functions, there is nothing to ellipticize. So it's expectable that at the sure point, the dependence on omega would drop out. What's more interesting is that the dependence on Q also drops out. You have seen this in the case of MacDonald polynomials. It is well known that MacDonald polynomials at the whole diagonal sort of, you have in the MacDonald case, you have a whole two-parameter space of parameters, and at the diagonal of that space, when T is equal to Q, there is no Q dependence. This is a well-known fact.
Sorry, Shamil, I'm a bit confused with your remark. You say that the Hamiltonians would still depend on P and omega as on parameters, but their eigenfunctions will not depend neither on P nor on omega.
That is correct, yes.
So does it mean that if you expand Hamiltonians in P and omega, then these would be eigenfunctions of each term? Of
yes, actually, I think the terms will be equal in this case. There is some degeneracy going on.
And so, and this is this Q equals to T.
Yes.
But I don't understand. I think your operator of Z will be just trivial in the case Q equals T. It will just a conjugation of some shift operators with just elliptic Vandermonde determinant. So
of course, this is not complicated at all.
So in some sense, you could just found eigenfunctions completely explicitly, yes?
That's exactly what we're doing, yes. So I'm just saying that series expansion, I'm just illustrating this case. I'm illustrating, using this example to illustrate the general statement that series expansion, even though it's not global, is useful to come up with global results in the cases when they exist. And then it may be easy or it may be hard to prove these results. So in this case, the result is going to be an easy result. It's not hard.
Can you show this formula, which what Andrei said is that it is conjugation of some Vandermonde determinant?
Yes. So here, if you take a look at this power series, O of Z,
yeah,
you can see that in the case when T is equal to Q, the shift here is Q to the Ni minus Nj. And this is exactly what is the shift produced by these operators from the right. So you can commute, you can take through, you can take these shift operators and pass them through the Vandermonde to the left. And this will result in this factor being removed from the function.
I see. Thank you.
Okay, but what I want to demonstrate is how this works at the level of the series. Indeed, you have a Q dependence here. but that Q dependence is trivial because you can see that it appears in the terms which have the same form as the original terms in the zeroth order. Here you have the original character x1 plus x2, and here you do as well. What this means is that this is nothing else but multiplying by a constant, which depends on some on parameter p. And what this means is that up to a constant, it's as if these terms are not there. So you can see from the series that the W dependence drops out and the Q dependence drops out. And the only dependence that you have remaining is P dependence. And then looking at the remaining series, it's not hard to guess that the corresponding dependence is a theta function. However, the theta function should appear in the denominator. And so in the case when t is equal to q, that formal expansion that I showed you turns into a global result, which is an exact formula given here. And due to the degeneracy that we discussed in the general case, this also works perfectly well in the general case. And the sure case of DELL eigenfunctions can be given fully generally. It's the sure, the character of the reducible representation lambda, the sure polynomial, times this simple prefactor. But I want to emphasize that even though this formula is trivial in a way, it also shows qualitatively what is the global behavior of the eigenfunctions of DELL. You should think about the global behavior of these eigenfunctions as the same as the inverses of theta functions. Yet, in the general case, when t is not equal to q, I was not able to find any satisfying expression in theta functions that would be global for these eigenfunctions. It is likely that such an expression will have to be an integral formula.
Are these functions symmetric if we permute xi and xj?
Yes.
Is it possible to somehow expand in the difference between q and t? Like in case when q equals t, we know the exact answer, and when like take some q divided by t minus 1 as parameter and expand
Actually,
it.
This is an excellent question, and surprisingly, I haven't tried this. In usual MacDonald theory, sometimes there are two ways to do this. Sometimes you expand in the power of q minus t. And instead, sometimes you specialize t to an integer power of q. So in a sense, the point t is equal to q is a member of the family t is equal to q squared, t is equal to q cubed, and so forth. And generally, t is equal to q to the beta, where beta is an integer parameter. And somehow it happens that integer values of beta are distinguished. So this would, in other words, in this language of this integrable system, this means that for Kalloger and Moser, there are distinguished integer values of the coupling constant. And it often happens that there are statements which are valid for t is equal to q, and there are other statements which are valid for t is equal to q squared, but not generally. So this is another way of approaching the point, the sure point, from the general MacDonald theory. And I tried the second one, but I haven't tried the first one. So expanding in t is equal to q is probably a good idea. I should try it, and everybody else should try it. Okay, so so all of this was to illustrate that the series expansion, even though it's not global, is useful for some things. You can check ideas and you can study some simple properties of these functions using series. Yet, of course, an explicit construction is desirable. So it would be nice to have, even if in series, it would be nice to have the series known to any order. And also solving these Hamiltonians that we suggest here in power series was not how we found the eigenfunctions in the first place. This is not how it was done by myself and Peter Kortiev. In fact, the actual road was inverse. We first had the eigenfunctions explicitly, and then we asked ourselves, what are the Hamiltonians for which these eigenfunctions are corresponding eigenfunctions? So what are the quantum operators which are diagonal in this basis of bounded polynomial power series? And this can be answered if you know a construction for the eigenfunctions.
Sorry, and where from these functions come?
These functions come from the relation to physics/geometry.
Of physics of what?
Of supersymmetric gauge theories with surface defects. So this is my next two slides. So because I only have 20 more minutes, correct?
Well, it's approximate, yeah.
Yeah, because of time limitation, I will not give any explicit formula, but I will guide you to the right formula in the literature. This is just a review. So, but it's interesting because it shows how modern physics and geometry give tools to study old problems. So in this case, they give tools to study many-body quantum integrable systems. So, so to start the review, it has been long known that supersymmetric gauge theories of certain class, and when I say certain class, I mean a certain number of supersymmetry generators, in this case 8, can be related to many-body integrable systems. So these are theories in 4 dimensions, 5 dimensions, and 6 dimensions with these historical supersymmetry labels. So the relation goes like this. It's a relation due to Seiberg and Witten. It's called Seiberg-Witten solution. And to each theory, it associates a spectral curve of a classical integrable system. In fact, it associates a spectral curve and it associates a curve. And then it turns out that this curve is a spectral curve of some classical integrable system. One way to see this is through geometry. So maybe personally appealing to me. So geometrically, the partition function of those supersymmetric gauge theories can be found as an equivariant integral of an appropriate characteristic class in cohomology of a variety. You have a variety which physically has a physical meaning of the moduli space of instantons in a given supersymmetric gauge theory. So usually it's singular, so it's not really a manifold or a variety even, but I call this variety for simplicity in this talk. And then what you can do, you can study equivariant cohomology of that variety, equivariant with respect to the torus action. And you have a natural torus in the problem because for one thing, these theories are defined on a space-time, which is sometimes in the 4-dimensional case can be thought of as C cross C, and then each complex plane can be multiplied by a small C star parameter, and these two C star parameters that you have here, well, in 4 dimensions, they are going to be rational, so not exponentiated, but in 5 dimensions, when you have an extra small circle in the space-time, these are exactly the two parameters Q and T in the integrable system that I'm talking about. So you multiply one of the planes, one of the complex planes by Q and the other one by T, and this gives the torus action, and you can consider equivariant cohomology with respect to that. And actually, I'm overstepping myself again because this is already a 5D case, and so it would be equivariant cohomology in 4 dimensions. It has to be K-theory in 5 dimensions and elliptic cohomology in 6 dimensions, such as the dictionary between physics and geometry. Well, the partition function can be represented as an integral of an appropriate characteristic class, which actually depends, the reason why I write appropriate is that this class depends on the choice of matter content. You can consider supersymmetric gauge theories with different kinds of matter. It could be fundamental matter or a joint or something else, no matter at all in principle. And for each choice, you have the corresponding quantity to integrate. And then you finally take an equivalent integral of that, which by famous theorems in geometry can be represented as a sum over fixed points of the torus action in equivalent cohomology. And these fixed points are labeled by discrete data, which is none other than these Young diagrams that we were talking about here. In fact, in realistic theories, it's not labeled by Young diagrams, but rather labeled by sets of Young diagrams, many Young diagrams, finitely many Young diagrams. Even though this may sound complicated, in fact, this is beautifully simple, and the resulting formula is an explicit series, a sum over sets of Young diagrams. And the statement of the relation to integrable systems is that the partition function of the theory asymptotically, in the limit when you switch off the equivariant parameters of the action, the leading asymptotics of that partition function is a function called prepotential, is related to a spectral curve of an integrable system in the following way. You have a certain simple canonical differential on the curve, and you have integrals of that differential over A cycles and B cycles. And then the integrals over A cycles can be parameterized as variables AI, and integrals over B cycles are then derivatives of a single function f over these variables AI. So that is a relation of the geometrically defined partition function of the theory to integrable systems here.
Sorry, Shamil, and since we have shortage of time, etc., can we, instead of all these words, can just pronounce two words, Nekrasov function?
Yes, yes, yes. And yes.
Okay, so Nekrasov function. And can I just say so that this eigenfunction you are looking for, you started with, yeah, it's equal to what? To Nekrasov function of some theory?
Exactly, that is the content of the second.
Just present a strict definition.
Sure, so that is the content.
Without any explanation, because to those who know, you can explain, to those...
Sure. So the reason for this slide is that I wanted to say that there is a relation, a long-known relation between the supersymmetric gauge theories to integrable systems. I explained it through Nekrasov function, and then the partition function Z is known as the Nekrasov function. And then this relation is to classical integrable systems. What we want is a relation to quantum integrable systems. And that is not hard either. What one needs to do is one needs to study these same gauge theories in the presence of a codimension 2 defect. Now, what is how does this work? There are many different formulations of this defect. You're adding a small extra bit into the theory. You can think about this as a submanifold. You can think about this as a coupling to a lower dimensional gauge theory. There is one way which is simplest, in my opinion. You consider a theory on orbifold of a discrete action by some Z, D group, and you compute the Nekrasov function on this background. So the partition function is still, everything is the same. It's still an equivalent integral. It's just the variety gets more involved and the torus action gets more involved. But other than this, it's the same. And the statement is that in the limit, which is called the Nekrasov-Shatashvili limit of vanishing equivalent parameter, the partition function, the Nekrasov function on an orbifold is an eigenfunction of the corresponding quantum Hamiltonian. And that is a construction that I'm talking about. This is a construction because equivariant integration techniques provide for you explicit power series expansions in Young diagrams, labeled by Young diagrams, for the unknown wave function, for the eigenfunction in question. It's explicit to any order in P and W, as opposed to the expansion that I was writing here. But the first few terms, of course, will match. They are going to be the
Sorry,
same.
once again, so you have to take 6-dimensional gauge theory For double.
For DELL, we have to take 6D, but this statement is general.
Yeah, 6D, and then you have to to put it on an orbifold.
Yes.
And then you know that in Q equals to T, so what is it, self-dual background?
Yes.
And you have this formula for this partition function with defect, which is just something divided by product of theta functions.
Yeah, that is correct.
I see.
So this would be a result for the Nekrasov functions on an orbifolds at the self-dual point.
I see.
However, you have to keep in mind that this is sorry, this is completely wrong. I apologize. The parameters Q and T in the construction are not related to the two parameters. These are not the same parameters as one of them is an equivariant parameter. The other one is not the equivariant parameter because the second equivariant parameter in the Nekrasov-Shutashvili limit is sent to 1.
I see. So it's quantum system. So there is only one Nekrasov parameter alive. And who is second parameter?
The second parameter is the mass of the adjoint matter.
Mass of the adjoint matter.
So it's not self-dual point. It's the point when the mass of the adjoint matter is related to the.
Thank you.
Okay, now it's correct. So see this equation in our paper with Peter for an explicit formula. And this concludes the discussion of the quantum DELL model because we have described both the Hamiltonians here and the eigenfunctions explicitly, at least at the level of the power series. So global properties remain open, but at the level of the power series and of course, modulo the fact that this is a conjecture. But this at least is an explicit conjecture for the quantum DELL system. So I do want to, in the remaining few minutes, I do want to consider the case of SU2 explicitly because this is really enlightening. So for SU2, in the case of two particles, we have this operator O of Z in accordance with the previous formula. What's nice is that there is no product. There is a single theta function here. And you have only two modes to consider, O0 and O1. It's easy to see by periodicity that the higher modes are going to be equal to either O0 or O1. And there is a single Hamiltonian, which is O1 divided by O0 to the left. Now, if you expand the theta function in power series to put coordinates and momenta on equal footing, this is easy to do because there is an explicit power series expansion for the Jacobi theta function. What you will get is this power series here, in which it is easy to recognize a genus 2 theta function. So genus 2 theta function is a special function related to geometry of genus 2 surfaces in the same way, much in the same way as genus 1 function is related to geometry of the torus. It has at least two characteristics, A and B. And O0 is the theta function, genus 2 theta function with characteristics 1, half, 0. And the first operator is the genus 2 theta function with characteristics 1, half, 1, half. The arguments of the theta functions are the coordinates and momenta, respectively. So this is a nice formula because it's putting coordinates and momenta on equal footing. And then when you consider, it's important to say that genus 2 theta function has a period matrix. And for us, that period matrix is the following 2 by 2 matrix. The diagonal values are related to its ellipticity in coordinates and ellipticity in momenta, respectively. And the off-diagonal component is related to T, which is the coupling constant of the integrable system.
So it's generic in some, it's generic period matrix, yeah?
It's generic, yes.
And so this genus 2, it's not restricted.
Not restricted, yes. Mm-hmm. Well, you have to think about P and W as being small, but other than this, and you get the following Hamiltonian. This is the only Hamiltonian because the system has 1 degree of freedom. But what is nice about this is that this is a global formula. It's not a power series expansion.
Does anything nice happen when this period matrix is a matrix of curve with the genus 2, or we don't know about it?
Sorry, this is a curve of genus 2.
In genus 2 we have all period matrices period matrices of the curve genus. Okay, I get it.
Yes, this is the feature of the case of n equals to 2 particles.
It's even a hyperelliptic. This curve should be.
I don't hear the question.
It's not a question, it's a statement.
It's hyperelliptic, but here is no curve actually. Yeah, it's just some theta function.
No, Andrei, you can, in principle, you can reconstruct the curve from the period matrix. Any period matrix, 2 by 2.
You mean that it is theta divisor or something like that?
No, that's just it's.
But okay, probably here is no need in this curve. I don't
know. Probably not.
Mm-hmm.
So this is a global formula. This is nice, and this is also a formula that allows us to compare to the known pieces of knowledge about the DELL system. Most importantly, in this paper, Holwood and Braden give an explicit formula for the Hamiltonian of the DELL system with a single degree of freedom. And it's striking how similar these formulas are. So our formula looks like literal quantization, naive quantization of Holwood and Braden's Hamiltonian. Of course, one has to know from our computation or from somewhere else that these two operators do not commute. So actually you have to divide from the left. That's important to remember. But once this is said, this is a literal naive quantization of this formula. Except,
I mean, excuse me.
Yes.
As far as I remember, there was a double elliptic one particle system was supposed by Rubtsov also. Rubtsov and there was a 3 or 4 authors paper.
Yes, this is going to be discussed on the next slide.
Okay.
So this is one suggestion.
But when you say nice formula, a part of it, it looks nicely. Does it have, well, whereas when it is a single Hamiltonian, what can be nice about it?
Well,
any function Q and P is
it's a global operator,
right? Huh? So
it's a global operator.
Something in particular. What is in particular nice about this theta function?
It's nice that the only thing that I'm saying is that it's nice that it's not a power series, but a globally defined function. So we can study.
It converges. I see.
Mm-hmm. But what happens with this Hamiltonian? Is this modular invariant if you change the period matrix basis of cycles by symplectic transformation? Is it really a linear function?
Genus 2 theta function has periodicity properties, and then this would
it's not only periodicity, it has some invariance with respect to change of basis.
Yes,
some modular properties.
That's what I would expect, that there has to be a property like this for this operator. And then it would translate to some property of eigenfunctions. This is not done, but at least you can expect that such a property can be written. So the only distinction is that the characteristics are slightly different for our result and their result. But I think this is not an issue at all because it's probably a different parameterization, different choice of parameterization of the spectral curve. Or in the worst case, there might be some canonical transformation, but even this, I don't know. But the relation has to be very close. And so at the same time, in this paper in the year 99, these 4 people proposed a different looking Hamiltonian for SU2. And one of those people, I believe, is listening to us right now. And there are 2 main distinctions. So one is that the period matrix of our Hamiltonian is constant. Indeed, it's just these parameters here. While for the suggestion of this paper, there is no period matrix really, because it's written in terms of genus 1 functions. But if you think about the modular parameter of the torus as an example of a period matrix, that parameter was dynamical in that paper. It was dependent on the coordinate. And then there are further generalizations, more recent, which consider SUN DELL systems with dynamical period matrices as well. And our approach is kind of orthogonal to all of these in the sense that we always have constant period matrices. And second, the Hamiltonian of that paper enjoys a property of PQ self-duality, which while self-duality of our construction is not clear yet. And in fact, there is a recent paper by Morozov et al. Where they show that our system does not have self-duality, and then reconstruct the self-duality in some limit. So show that what needs to be done in order for the system to become self-dual.
Oh, it's almost obvious, because what we did long ago, we just had this as a motivation that all systems of Rosenar's family, they have some nice dual behavior. Yeah, like trigonometric Rosenars you started with is a self-dual system. And we thought the double elliptic system should be also self-dual in the same sense. And then we got this ugly formula you just mentioned with this period matrix dependent explicitly on dynamical variables. And since it is, well, it is already in the simplest case, so from this point of view, there is no chance, I think, for your Hamiltonians to be self-dual in that Rosenar sense. But maybe they're dual in some other manner, I don't know. Nikita, you wanted to add something or not?
No, it's a random sound. Sorry, I'm sorry. I just joined in. I probably missed already heated discussions.
Okay, thank you, Andrei, for your comment. So I want to conclude by saying that relating various formulations for DELL remains an interesting direction for the research. But to the best of my knowledge, these operators here remain the only formulation of quantum DELL system that we have at the moment. So the other formulations have considered classical DELL systems. And I also wanted to comment a little bit about limits to when one of the elliptic parameters degenerates to 0. If time allows me, and if the organizers allow me, I will say just a few words about this. So in the limit when omega goes to 0, you get much simpler expressions for the Hamiltonians. This is, of course, well known. This is the elliptic Rudjuna-Schneider model, so-called. And you can see that what you do, you ellipticize the signs, the sign functions and the coefficients, and you keep the shifts intact, so you do nothing to them. This is a very useful system. So in particular, for example, in physics, just a random application, they compute superconformal indices of theories and spheres, and eigenfunctions of the system are used in this computation and are useful in this computation. One remarkable property of
by the way, is this an experimental fact, or it's derived for some principles that the Rosenar separators annihilate the superconformal indices?
From what I remember, in their paper, this came from the fact that these indices have to satisfy difference equations, and then they derive explicitly the formula for the difference equation, and it happens to be this formula. One remarkable property of these W goes to 0 eigenfunctions is orthogonality. And so this is kind of global. So this is the only property that I know that is not order by order, but rather exact in P. And it goes like this, that these functions form an orthogonal basis of functions, or simply are orthogonal with respect to their indices lambda and mu, and you integrate with respect to the scalar product, which is given by this product of theta functions.
What is beta?
Beta is parameterization for t skew to the beta. So here I'm writing this for an integer beta, actually. In principle, beta may be not integer, then you will have an infinite product, and this can be expressed as a ratio of elliptic gamma functions. So this is still pretty good, I would say.
So I want to ask, are there any kind of closed formulas for this eigenfunctions for integer beta?
For beta equals to 1, you've seen it. And other than this, I don't know. And I was not able to find.
Even for elliptic algebra, yes?
Even for elliptic algebra, I don't think so.
Thank you.
This would be something like elliptic jack functions, and they are not much simpler than elliptic MacDonald functions. So the other limiting case is when p goes to 0. In this case, you can also write simple expressions for the Hamiltonians, but in this case, you already need to have this peculiar current OZ that we had in our paper with Peter, because O0, the zeroth component of the current, is not anything simple. The distinction is that OZ can be explicitly summed. So if you remember, it was a sum over a lattice, and that sum in this case can be simply summed to a product of theta functions.
Sorry, Shamil, and where is z in the right-hand side?
Oh, that's right. There has to be a z. I think it's a theta function of z times everything else. It's a misprint. So here instead you have a sum over permutations. Of course, for given n, there are finitely many. And it's this. And the remarkable property of eigenfunctions of the system is polynomiality. They are just as usual MacDonald polynomials, or just as usual Schneider system, the eigenfunctions are literal polynomials. And I show an example for the third symmetric power of the fundamental representation. It's a 4 terms again, but now the terms are ratios of theta functions. It's quite nice. Orthogonality is a curious thing here. So for orthogonality for these eigenfunctions is also known, but I think is new. It relies upon identities for theta functions, and I haven't found any reference in the literature to this. So for SU2, just briefly, I show the slide that if you write eigenfunctions for SU2, then the orthogonal functions can be also written down explicitly here. And what's kind of curious is that these orthogonal functions are deformations together of the eigenfunction times the measure. So for these functions, you have separately the measure of orthogonality, and then you have product of two functions, and this is orthogonal. But for these functions instead, the orthogonal function absorbs the measure into itself. And then the product of the measure times the function is deformed with theta functions ellipticized nicely. So this is the first example that I've seen where this works like this. And it's interesting to see what happens in the general SQM case. I'm sure that it can be worked out. And then, of course, it's also interesting to see what happens with orthogonality for the general case when both elliptic parameters are switched on. You can expect, since in this simple example, the measure is absorbed, you can also expect this to happen in the full case as well. And then this also remains to be worked out.
Do we have some combinatorial sense of these functions?
I didn't hear the question.
Some combinatorics, is it somehow discovered from combinatorics formulas?
I don't think that in combinatorics works, there have been much work on elliptic functions. Or at least it's not, I'm not familiar if they exist. with this, I think I would like to thank you for your attention. I'm out of time. Thank you.
Thank you.
Thank you. And I have
Thank you. And
thank you. I have a question. Is it possible to is it in any sense generalized not to A series but to B, C, or something like that, or other classical?
Definitely has to be possible, but we didn't do this. I don't.
Is it clear from what we can start, or like? Or
well,
from...
this formula is kind of suggestive. So I haven't thought this through, but structures such as van der Monde determinants are easily generalizable. For example, the sum over permutations is also strongly suggestive of AN type. Okay. Here.
More questions?
I apologize if my question was already answered by the talk, but so these Hamiltonians which you suggested, did you derive them from somewhere, or you just
yes? So this is contained in these two slides. Okay. We derived them, myself, in relation to physics/geometry. So we considered a supersymmetric gauge theory in 6 dimensions in the presence of a codimension 2 surface defect. And then we computed the partition function of this defect coupled to the gauge theory in the limit, in the Nekrasov-Shutashvili limit, when epsilon, one of the equivariant parameters goes to 0.
Okay, that's the standard setup, but did you actually prove that this partition function of the surface defect is an eigenfunction of the operators which you wrote?
No, we only found the operators.
Oh, so you found them by expansion and just it's a guesswork. So it's a guess. It's a conjecture. It's not a statement. Okay.
We asked ourselves what are the operators that diagonalize this.
Sure. Okay. Thank you.
Other questions which have not yet been asked?
Yes, so I wanted to ask.
I apologize.
So is there any commutation relation between OKs themselves without division by O0? So just to understand what is the meaning of this phenomenon that we should divide by one of the operators?
I don't think so. So you can, of course, formulate these relations between these operators as the relations between O's. And in this case, you will get something like something of 4th order, which is not really very much comprehensible and I don't think contains much more information simply than commutation of H's.
But are there any similar phenomena somewhere? I don't know how to ask it.
Pash, of course they are. If you take Toda's coordinates, they are ratios of the theta functions, and they do commute. So the ratios of theta functions commute with respect to the variables, well, dual variables, the periods and the angles. And ratios is important. So it's a very rough analogy, but briefly it comes out of this.
And do we know commutation relations between that theta functions for Toda or not?
No, you can substitute to the bracket and see what they are. I don't think that they are especially good.
I see. Thanks.
Sorry, Shamil, maybe you wanted to say something different. Just
no, I agree. I know this example. I think it's analogous a little bit.
So thank you. Any more questions?
Maybe.
There were many good questions, right?
Yeah, bad and stupid questions. So if referring to Nekrasov and Shutashvili functions, so if you say that you take the limit.
There are no such functions. He was referring to
okay, yes,
actually,
I'm stupid
already that the functions of the same name as you appeared before you at this seminar.
Okay, but nevertheless, so if you will not take the limit as one of these parameters going to 0, then can you make some generalization of this stuff, or you don't see it?
I didn't try, but to the best of my knowledge, they are not anymore related to the integrable system in question. Maybe Nikita wants to add.
Well, it's we know that if you take a limit when you are when one of the elliptic curves degenerates, so you have if you become rational in the momenta, then what you get is the canonical homologic of Bernard equation on the torus.
Ah, I see.
So it's and of course the expectation is that if you become trigonometric, so the non-stationary version of elliptic Roisenars would be the QKZ on the torus, and the double elliptic version is of course very interesting. So it should be some equation which is related to the elliptic quantum algebra, elliptic quantum group. So there's some equation obeyed by the traces of intertwiners, specific intertwiners in this case for the elliptic quantum group. But I don't know how to prove this statement already in the trigonometric case. I mean, the tricks which we have in gauge theory, they use rationality very for the moment they use rationality in a very crucial way. And the relation to superconformal indices, it's also fascinating, but I also don't understand it. So it's I was not sure that people like Rastelli and Gaiotto derived anything. But maybe they have. That's why I asked you.
Okay.
Yeah, I have a question. Does the system have something like double invariance of limits?
Yes, this is exactly what we're working right now with Peter. You can take a limit when t, this mass of the adjoint in physics, or the coupling constant in the integrable system goes to 0, not to 1, which would correspond to decoupling, but to 0 actually. So that would be, I think you can think about this as infinite coupling. And then simultaneously, you also take the elliptic parameters to 0 or to infinity, depending on where you look. And also you rescale the variables, the x's and the p's in a proper way. And then you get a kind of a scaling limit, which is a completely different integrable system. It's of Taylor type, which is expectable because then you would land into a pure gauge theory that wouldn't have a joint matter.
Yeah, but I think so. That's expected, of course. But I think the question was about taking the similar limit for the other elliptic curve, for the second elliptic parameter.
Yes, there is.
So for that, we don't have a gauge theory interpretation, do we?
Why not? This Hamiltonians have been derived from gauge theory with two parameters.
No. The question is about if you degenerate second elliptic parameter, which has no sense of the mass.
No, but this is a simultaneous limit. So you degenerate the mass of the adjoint, and then simultaneously you take a limit of the two elliptic parameters.
Of both elliptic parameters.
Yes.
Oh. Okay. And what does it correspond to in gauge theory?
One of them is this the instanton parameter for the 6D. Sorry, one of them is the instanton parameter of the theory, and the other one is the parameter that counts that is responsible for the 6 dimensions.
Yes, of course. But why would you expect the double scaling limit when you tune the mass? So the mass goes to infinity, even though it's an elliptic parameter now, and the elliptic curve generates. Why do you expect anything simple on the gauge theory side?
I see. Probably not. Yeah.
I mean, it's if you have a non-trivial limit, it's very interesting, but it's far from obvious that it has a gauge theory interpretation. But also, how do you take so the mass right now it lives on elliptic curve, right?
The t?
Well, the log of t is like
no t is lives on a circle.
It's But I thought the mass. So the mass is it's a Wilson loop for the flavor symmetry.
Okay.
So it's like a flat connection for the flavor symmetry on the torus. So it naturally it lives on the elliptic curve on the dual torus, if you like. Don't you have an invariance on the? So if I multiply t by I guess by p in your notation, don't you get some? I mean, aren't you Hamiltonians invariant under that? Or
Well, this may be answered by this slide.
I'm sorry, I missed most of the slides.
Oh, they do not seem to be invariant. Yeah.
So
but as a set, are they maybe covariant?
We have this nice formulation for SU2. We have this nice formulation in terms of genus 2 theta functions.
Okay.
It's global in the sense that our operators are exactly written not as power series but as genus 2 theta functions.
And if I remember correctly, the Zabel-Quitten curve for the SU2 theory,
yes,
six-dimensional SU2 theory is also genus 2, right?
Yes, so that is this slide here.
Okay.
So our Hamiltonian looks like naive quantization of the coordinate on the moduli space that Hollowell and Braden wrote explicitly.
Okay, but that's saying that there are it's the opposite statement. You're saying that there are further duality transformations than you just. So the modular group for genus 2 curves contains the product of modular groups for the elliptic curves. If a genus 2 curve is almost like it's almost degenerate.
Right. But what I wanted to say is that here you can see how the mass of the adjoint, the exponentiated mass of the adjoint enters the geometry of the genus 2 curve. Yeah. So the period matrix of the theta functions that we have, the diagonal components are the elliptic parameters in the coordinate and momenta.
Yes.
And then the off-diagonal parameter is the mass of the adjoint.
Right.
And you tended to 0, you said, yeah?
No, but before we tend to 0, I'm just wondering what happens if I multiply t by p. So it's like maybe it's some.
I would expect some 2-by-2 transformations here to be relevant. So you see that.
Yeah, sorry, Nikit, you mean some den twist or what?
It's a large gauge transformation. It's a large gauge transformation. So I'm not performing the modular transformation on the curve, but I'm modifying. I'm changing the mass by shifting it by a lattice, by an element of a lattice. Mm-hmm. It should be an invariance of the theory because if we compactify from 6 dimensions on the torus, then the mass is not a number. It's the expectation value of the Wilson loop, and so it has to be the theory is invariant under the shifts of this mass parameter by 2 periods of the elliptic curve, which corresponds to the compactification, not the instanton one, but the geometric one. Unless there is some anomaly, maybe what? But I don't think there's any anomaly.
I suspect that for genus 2 theta functions, there are properties, transformation properties like this. That if you multiply t by p, then
yeah. So it might I'll answer down. So maybe from the point of view of genus 2 curve, it is a den twist. But the genus 2 curve is a kind of it's an effective object. It's not. I mean, well, for you it's. So this Hamiltonian, which we see on the slide, does it correspond to epsilon 2 to 0 limit? It's
yes, that's the Hamiltonian that governs the epsilon 2 to 0 limit in the gauge theory.
So t is actually it's an exponential of the mass divided by epsilon 1, presumably.
Yes.
Okay. Okay, so it's probably even more involved because also epsilon 1 gets permuted. Okay, thank you.
Okay, so maybe last question, Kolya. You wanted to say something?
Yes, but I think that in discussion it's already have been discussed. I wanted to ask about modular symmetry, but it was discussed.
Well, Shamil already said in the talk that it's a hard question. Okay, so thank you very much.
Thank you. I had a small question, if I may. Is there any way to take a look at who participated in the talk?